Right. So let's look at the unit number 4, which is probability theory. Just as I introduced the course when I was introducing it, I did indicate that at some point we would talk about probability theory. And so the time has come that we need to talk about probability theory. By basic definition, you do define probability as the likelihood of an event to happen, right? The likelihood of an event to happen. We know we don't dwell in the future and we don't know about the future. So basically, most of the events that we have that will occur ahead of us, we are not certain about them. And because we are not certain about them, what usually happens is that we just have to measure how likely that event or that occurrence, the phenomena is to happen. So the measure of the likelihood of an event to happen is called probability. Is that clear? Right. Are you able to hear me? I think your mic is off. Maybe.
Yeah. Okay, I can hear you.
Okay. Right. Thank you. So what probability tells us is how likely something is to occur. And the probability concepts are also central, especially to inferential statistics. Okay. Yeah.
Yes.
So inferential statistics, which is the statistics where we draw conclusions after observing the behavior of data, and the probability concepts are really important. So we may be aware that probabilities always range from 0 to 1, okay? Probabilities range from 0 to 1. You will never find an answer that is after 1 or the answer that is before 0. That's a negative answer. Probabilities shall never be above 1 and shall never be a negative answer. That is what the point indicates. That's clear.
All right.
So 0, we say the probability is 0 when there is no chance of an event to occur. And then 1, we say the probability is 1 when, we are certain that the event is going to occur. We say the probability is 1. Most of the times we say that the probability is 1 when we are really certain that it will be like that. But again, we say 0 when we are sure that it will not happen. Yeah, it will never happen. Okay? We are really sure about that. So now, most of the probabilities usually do not dwell in these extremes. It's not usually easy to be certain about the event not being not occurring or it occurring 100%. So usually there are some elements of doubt. So probabilities will just be between 0 and 1, some numbers in between.
Oh.
So in oftentimes we interchange probabilities and percentages. We use them as the same, but probabilities refer to a single event, while percentages refer to the portion of repeated events that we get the outcome we are interested in. Right. I'm showing you the difference between probabilities. Many people have been using probabilities and percentages as the same, but probabilities refer to the single events, while percentages refer to the portion of repeated events that we get the outcome we are interested in. That is clear.
Yes.
Okay. If that is clear, then let's say now we say that there is a 0.329 probability of it raining in March, or 32.9% of the time in March it rains. So this is the interpretation. So you can say there is the probability of 0.329, okay, of it raining in March. Or in other words, we can say there is a 32.9%, which is just this same number times 100, all right? Just multiply this decimal by 100 and of it's raining. In oftentimes, the probabilities of events are symbolized by P and the name of the event. Okay? So in this case, the probability that it will rain will be given a probability that it will rain. Let's say A, it will rain, plus the probability that it will not rain, that's a probability of A complement. All these added together, they should equal 1.
Okay.
So when you sum together the probability of an event to happen plus the probability that the event will not happen, they should all equal 1. Okay. So for example, we have said the probability of it raining is 0.329. Then the probability of it not raining, let's say A complement. When you sum the two, it should equal 1. So we make the probability of A complement the subject of the formula. And so we shall have the probability of A complement 1 minus 0.329. And the difference we get is what?
Hello?
What's the probability?
Okay, just can you repeat
Okay.
the explanation?
I was just from saying that we have the law of complement probabilities. It says that the probability of an event to happen, let's say event A, plus the probability that the same event shall not happen, let's call this A complement. When you add them together, they should be equal 1.
Oh, okay.
So in the case where we are given the probability that the event will happen or occur, for example, it will rain, then we ask you to find the probability that it shall not rain. We'll use this same rule and we'll come up with the answer. So let's say we are given the probability that it will rain being 0.329 plus the probability that it shall not rain equal to 1. Then we want the probability that it shall not rain. So the probability that it shall not rain will be 1 minus 0.329. And what is the probability thereof?
Oh, okay. 0.671.
0.671. Right. 0.671. So would say about 67% is the probability that it will not rain, right? So meaning we have a larger percentage or the larger chance that it will not rain as compared to that it will rain. So that is the law of complementary probabilities.
Okay.
Now, there are two basic ways to find simple probabilities. One way is to find a probability, to find a probability is a priori, right? Or maybe, let's say, using logic without any real world evidence or experience. So here we are trying to use logic without any real life or real world evidence or experience. So let's say we want to know a die is that is fair-sided, so it is tossed. Let's say, you know a die?
Yes.
Yes, that you didn't play that game. You remember those games we used to play?
Yes.
So what is the probability that it should give you 1 out of 8? Out of 6 sides. So it shall be just 1 divided by the 60, the total 60 sides. So the probability it shall be 0.167. This probability is a probability that it shall land on one side, like on the part that has 1, side that has 1. If you want the one for 2, you check where there are 2. How many 2s are there? You just have 1 as well. So that's basically how it occurs.
Oh, okay.
What if you ask that if you roll a dice, what's the probability of getting an even number from the die? So a die has got the following sides: 1, 2, 3, 4, 5, 6.
6.
So what is the probability of getting an even number? You know what an even number is?
Yes.
What is an even number?
An even number. It could be
Yes,
246.
yes. So an even number is a number divisible by 2, right? The number that is divisible by 2 is called an even number. Okay, so in this case, we have how many even numbers?
3.
Yes, 3 even numbers. Out of how many numbers are there? There are 6 altogether. And so you have half is the probability of getting an even number when you roll the dice. That is clear.
Yes.
Okay. So what is the probability of getting an odd number?
An odd number.
You know what an odd number is?
A number that is not divisible by 2. I think.
It leaves the remainder one.
5, yes. 1,
Yeah.
3, and 5 in this
1,
case.
3, 5. So it will still be 3/6. It's still giving you half. So basically, this is what we call using the first way of finding the probabilities. Right. So basically, the formula would be of finding the probabilities. We can say the probability of favorable outcome, the favorable outcome divided by all possible outcome, isn't it? The favorable outcome over all possible outcome. And that is how you find probabilities. So for example, the favorable ones we had was to find the even numbers, and there were 3 in number. Divide that by 6, and that is what we had.
Okay.
Now, if that is the case, then the probability is the number of ways your outcome can be achieved, okay, over all possible outcome that I have already indicated. Then the second method to determine a probability is called the posterior method, right? The posterior method. Now, this uses the experience and evidence that has accumulated over time to determine the likelihood of an event to happen. Right. So this one, the posterior, remember the other one, the previous one was not using any evidence, any experience. Yeah. But this one, we are riding on the experience and evidence that has accumulated over time. Okay, so that we can determine the event, the likelihood of this event to happen. So for example, if we do not know what the probability of getting a head is, the same as the probability of getting a tail when we flip the coin once, okay? So we cannot use the previous methodology to do that. So we can flip the coin repeated several times. After flipping the coin, let's say 6,000 times, if we get 300 heads, you can conclude the probability of getting a head as what? 50%.
Yeah.
Right. But it is not always that it will be like that. So what we are having now is that in a situation where the probability of getting a desired output for a given event, for trying it maybe of course once, just doing the experiment once. Then we are asked to assume that now we do the experiment several times. what is the probability of getting the desired output? That's a question we usually have. So if you have a coin, right? If you throw a coin once, the probability of getting a head is 0.5%, isn't it? It's 1/2.
Yes.
Right. But what if now you throw that coin 100 times? What is the probability that you get 5 heads? Like in 5 times, you're going to get a head. So those are questions that we get to have. What if you throw it 1,000 times? You may not keep on repeating that experience, that experiment several times. So you need some advanced methodologies to use here. And that leads us to what you call the probability distributions. I just observed that in your notes, there is only 2, they just talked about only 2 probability distributions. Really, I don't know. Right. So sometimes we want to look at probabilities in a more complex way. So we suppose that we want to know the probability that it will rain on the end of the day in March, given that it rained on the previous day. You've seen that. So those probabilities are called the conditional probabilities, right? We want to measure the probability of an event to happen, given that the previous event happened. So we are riding on the fact that another event has already happened. What is the probability of that event to happen? Mathematically, you can present this as what is the probability of an event A happening, given that event B has occurred. Right. So that is what happens most of the times. Yeah. Someone says that, okay, given that this person smokes, what is the probability that they drink? You know, you're riding on what is already existing. That is what we call conditional probability. There is already an underlying condition. Okay. The other type of probability that we often want is a joint probability. Now, if a joint probability, it tells us the likelihood of 2 or more events occurring at the same time, right? Like both of them. That's called joint probability. We can suppose you want to know the probability that you will like this course and that you will get an A in it simultaneously, right? Like it plus get an A. You may like it but not get an A. Now, like and get an A. These are 2 events, different events. They are occurring at the same time. We call these as a joint probabilities. Now, the formula for the joint probabilities is given as following. The probability of getting an A, of liking the course, which is event A, intersection, meaning combining, happening at the same time, with the probability of getting an AB. This will be given as, you're following?
Yes, I'm following.
It will be given as the probability of A times the probability of B given A. Or you can say it should be given as the probability of B times the probability of A given B, like that. That is the formula for finding a joint probability. Okay, so we do it like that.
Okay.
Not very much complicated. Any question?
No question.
Okay. Now, the probability of 2 events occurring at the same time is the probability that the first one will occur times the probability the second one will occur, given that the first one has occurred. This is just an explanation of what we said. Okay. The probability of these 2 events occurring at the same time is given that, okay, the probability that the first event occurs times the probability that the second event occurs, given that the first event has occurred. Now, if the events are independent, the calculation is even easier. You know what independent events are?
Yes, they are not related. I don't know, independent, they are separate. I don't know how to
Yeah,
explain it, but there's no relationship.
yeah, there is no relationship as basic as it is. Thank you. So the independent ones, the occurrence of the other event does not affect, the
Mhm,
occurring of the other event. With no relationship whatsoever. Now, can you
mhm,
suppose you want to know the probability of liking the course and not needing to get um, gas on the way home,
mhm.
right? What's the relationship getting gas on the way home and liking the course? Really,
No
these are not,
relationship.
there's no
Yeah.
relationship whatsoever. We call these as the independent events. And those
Independent.
events are presumably independent. So the probability of B given A is equal to just B, right?
Mhm, mhm,
Mm-hmm. So that is how it is. So you just have to do that. No need
mhm,
of suffering.
mhm,
Now, the final type of probability is the union of two probabilities. Now, with the union of two probability is the probability that either one event will occur or the other will occur. So usually when you're dealing with the union of probability, we add the probabilities.
Oh, okay.
Mhm. Now, so this is the probability, this is the formula for such union of probability. Let's say probability of given A union B shall just equal to the probability of A plus the probability of what? Of B minus the probability of the intersection between the two. That's the union of the sets.
Mhm,
So whenever you are asked to find the probabilities for the union, for the uniting events, yeah. So you just have to add the two events and remove the probability that they can occur at the same time.
mhm,
Sometimes you may understand that it is easy to understand why we just add the probability of A and the probability, but it may be less clear why we subtract the intersection, right?
mhm,
So the answer is simple because we counted where they overlap twice. Those
mhm,
intersection parts,
mhm.
we counted twice. When you just count A intersection B, we are counting the figures that belong to A and those elements that also belong to A. So you remove those that are belonging in both, then you just have
Mm.
those for B and those for A, and then you'll be
Oh,
fine.
okay.
Mhm. So now sometimes the events are mutually exclusive. So if those are mutually exclusive, we do not need to subtract the intersection, okay? If they are exclusive. So mutually exclusive events are events that cannot occur at the same time. So there is no overlapping. Those are mutually exclusive events, right? More like the
Mhm,
disjoint states, like they can't occur at the same time. Their intersection is zero. Probability
mhm.
or event A and event B, you've seen them. There is no need of subtracting the intersection because these are mutually exclusive events, yeah?
Mhm,
Now, you see, let's see have this simple exercise.
mhm,
USA Today gave the information shown in the table about the ages of children receiving toys. So the percentages represent all toys sold. Okay.
mhm,
So there is 2 years and under, that is 15% of the toys. 3
mhm.
to 5, 22, 27 for 6 to 9, 22% for 13 and above. Right.
Right.
And now, what is the probability that a toy is purchased for someone 6 years or old or older, meaning 6 years and above? So what is the probability for getting 6 years and above? The percentages. Six years and above.
So 6 years and
Anyway.
above.
Mm-hmm. Anyway,
27%.
yeah, you just
Yeah.
go ahead.
Yeah. Should be
Right.
27%. Yeah. 14% and 20%.
27, 14 plus 22%. When you add all these probabilities or percentages, they give you that probability of getting, 6 and higher. Very easy. Yeah. And what is it that we find?
27 plus 14. 63.
Yeah, 63%, which is as good as 0.63, right? Probability. So that is how it is done. What is the probability of getting 12 years old or younger? 12 years old or younger, meaning 12 years old or less. So that's from below 12, right? 12 years or below.
Okay, so 14, 27, 22%, and 15%.
Yes, 12 years and below. And then between 6 and 12, between 6 and 12.
27% and 14%.
Yeah. And the 3 to 9?
22% and 27%.
Yeah, so as basic as it is. Any question?
No question.
Okay. You will be fine. And now, there is need for us to learn how to use the standard normal distribution to come up with the probabilities now. This is for the, we use this for the continuous random variables when the random variables given are continuous. So let's have this one. Now, if we want to find the probability of a score falling in a certain range, let's say between 3 and 7 or more than 12, we can use still the normal curve to determine that probability. So our ability to make that determination is based on some known characteristics of the certain of the normal curve, the standard normal distribution curve. It has got the following characteristics. The standard normal distribution curve, it has got these characteristics.
Okay.
Yes. So it says that most of the data, about to the 68.26% of the data set falls within the first standard deviation from the mean. Then 95.44 of data set falls 2 standard deviation away from the center, and 99.72 falls 3 standard deviations away from the center. So these are some of the characteristics of the standard normal distribution table. So now, to find out how many standard deviations from the mean an observation is, you get the point? Because this one has just been telling us that 60% of data is 1 standard deviation. Now we want to know how many standard deviations the observation is from the mean. Then we calculate the standardized value or the z-score. So to calculate the z-score, you use the formula. Z-score is equal to x minus mu, the mean, divided by the standard deviation. And now you have to follow nicely. I want to speak slowly here.
Okay.
So this is the z-score. What do we use the z-score for? We use it to find how many standard deviations from the mean and observation is, okay, from the mean, the average. So if you look at the formula, you can see that the z-score of 0 will put that the score at the mean. It will put the score at the mean. If let's say the z-score is 0, this z is 0. So it will just be at the mean like that. So the z-score will be here, like will be 0. That's what it means. Okay. Now, and the z-score of, let's say, 2.67 and the standard deviation of 2.67, this will be above the mean. And we will show you how to do these computations. Don't worry. Don't even panic.
Okay.
Let's look at a practical example we have. Yeah, at least here there is an a person, follow nicely the question. A person's blood glucose level and diabetes are closely related. Now, let X be a random variable measured in milligram of glucose per deciliter. Okay? Now, after a 12-hour fast, the random variable X will have a distribution that is approximate to that of the normal. With the mean, you remember the Z value, it was the X minus the mu over the standard deviation. So you need these to do the computation. So given that the mean, which is your mu, in this question is what? 85, right? And the standard deviation is what? 25, isn't it?
Yes.
Now, what is the probability that for an adult under 50 years old after the fast, X is more than what? 60. So we are looking for the probability that X is more than what? 60. So we need to convert this X. We need to measure how many standard deviations it is from the mean. So by so doing, we'll have to convert this 60 into a z-score. So X is 60 minus the mu, which is 85 divided by 25. What is the z-score? And now we follow nice. What do you get?
I'm getting -1.
Yeah. So the z-score is -1.00, right? Now, this is not a probability. This is just a z-score. Pay attention now to my explanation. So when you find the z-score is not an answer. They are asking for the probability. For you to find the probability that corresponds to -1.00, you have to go to the standard normal distribution table. Get the point? So let's calculate in advance the X value, the z-scores, then so that when you go to the table, we're just using the numbers. Then let's also do for B. So for the A is -1, right? And we're looking for more than 1. So we're looking for that probability for more than 1. I'll show you how to get it. Then let's do the second one. The second one is 110 minus 85 divided by 25.
One.
This one as well.
Yes.
Oh, interesting. Positive one.
Positive one.
Okay. So 1.00. Anyways, so we are looking for the probability that x is less than 1 here. Here is greater than what? Greater than 1. So this number is no longer 110. It's equivalent to 1. Get it like this. Now it's 1. Then this one is negative 1. Let's go to the table so that I show you a little bit before we can continue with the other questions.
Okay.
Let me go to the standard normal distribution table. Hoping that you were trained how to read this table properly, but anyways, we'll be fine. Yes. Are you able to see this table that I am using?
Can't see the numbers clear. Oh, okay. Okay. I'm able to see now.
You will be fine. You'll be okay. Look, huh? So now you are looking for the area where where z is equal to what? They have said z is less than negative 1. Less than negative 1.00, right? And where z is greater than 1 positive. So we want to look for the area here that corresponds to the first one, to negative 1 to negative 1, 0, 0. Okay. Let's look for that area that corresponds to negative 1. Now, when you find that area that corresponds to negative 1, so in this case, the standard normal distribution curve is like this. It's symmetric. So to be symmetric, it means that the right side is equal to the what? To the left side. Which means that the negative side and the positive side, they give you the same areas, like it's still the same. So in that case, when you come to the table, you treat this as 1. Okay. So we are going to come where there is 1. 1. So when you have this, this is the value, you have to break it down into 2 decimal places. So it will be 1, okay, 1.0 and the 0.00, isn't it? Like on top, the Z table has got 2 decimal places. Then here it has got 1 decimal place. So whatever number, for example, you have 2.53, you have to break it down to 2.5 and the 0.03. You get it? When you add these, they give 0.3. If you have a number 3.31, this will be 3.1 and 0.0 or what? 3.3 and 0.01, so that when you add 3.31. So basically that's what you do. So given the number that we have here, z equal to negative 1.00 or equal to 1, it shall be broken as 1.0 and 0.00. So you have to check where 1.1, where we have 1. What? Is it 1.0? The first one. 1.0 is in this line, isn't it? And then 0.0 is in which line? It's in here, right?
Yes.
Yeah. So now, follow nicely. This probability that we have found, it is 0.1587. This probability, is on the right side of the Z value that you have. Okay, it is just right on the right side. So for example, the Z value will sit like this. There is a positive number here, the Z critique positive, and the other Z score here, which is what? Negative. That's how they sit. So yours is negative. So here we are going to put negative what? 1, like negative 1 here. That's your Z score. So we are told that this probability distribution table, looking at the structure that we have on top, it just gives us the probabilities that are after the Z value, right? To the right and to the left of the Z value. Okay? To the right side here and to the left of the Z value here in the extremes. So when you are asked to find the area of which one? The area before -1, which is less than 1, less than -1. We are looking for which area? We are looking for this area. You get? This is the area that we are actually looking for. And this area has already been found, is equal to that. Because this right part of the equation, this green part, it is equal to this side, which we can shade. Like the table is symmetric. So the answer will be 0.1587. This is the probability of getting less than what? -1, isn't it?
-1. Yes.
Which is where x is less than 60 now. Remember where we started from. Less than x is 60, that is the 0.1587. That is clear. Now, we also have this one. The other one was saying Z is what? Is 1, greater than 1, right? The B1. Z is equal to 1.00. We can break this down as 1.0 and 0.00, which will still be, it will still be the same thing. It's only that this one is on the right side. These things have the same values. So now, look, we are looking for what is greater. Greater than what? This value. So it's only that now our number, our 1 will be this side. It will be this side. Yes. And so the area is this one that is on the right side. This is the area that is greater than this number. If they had been asking for what is less, you would have considered this part before this one. This side. But we're just considering this because it is right after this number. Is that clear?
Yes.
So now, what you're going to do is to simply get the same value. Since this value of already assessed, it is on the right side, it is on the greater side. So it is still the same answer. 158 is greater. But if the question had been asking for what is less, right? Imagine the question was asking for what is less than 1. Meaning would have been considering this. Now, get this property. Am I speaking so fast?
No, the thing is, I've never learned this before. I've never even seen this before. Yeah.
Okay. I get it.
Yeah,
Don't
we're only
worry.
at school for 2 weeks. And we are learning for 4 courses in that 2 weeks. Yeah.
Okay. Okay, now try to follow this IC. You need just a normal session, just a session only on how to read the table. But in that recording that I shared, there is explanation on how to read, just how to read this table on just how to read it.
Okay.
Just that. So you can follow it.
right.
There is this part. So on the right side, you just get this figure for the right side. Now, We know that the total area under this curve is equal to 1, right? The total probability should be equal to 1. So if you are given the right side as 0.1587, then to find what is less than 1, what is the less than this number, we just have to say total probability 1 minus what? 0.1587. So when you subtract this figure from 1, it will give us this area which is less than all this area up to the negatives. Is that clear?
No, okay. Yes.
That is what it does.
Okay.
So what is the probability? What would be the probability?
Negative 1.1587.
No, like positive 1. This
Oh,
one.
positive
1 minus.
1. 1 minus 0.1587. Oh, okay. 0.8413.
0.8413. So this is the
Yes.
probability for less than 1 or less than 6. Was that 6 or 110? Less than 110, yeah.
Less than 110.
Yes, that is how it would have been. So you read this standard normal distribution table to come up with those figures.
Okay.
Let me have the other one. What were the other ones say? Now, you will be okay.
Yeah.
Very fine. Okay. Now we want to for between 110 and that. So these are the same numbers that we had. For 60, it was -1, eh?
Yes.
We just have to convert these again. So it will be between -1 and the 1. 110, you found 1. So we want the probability of between -1 and the 1. Is that clear?
Yes.
How do you find that? Then you also need for the probability greater than 140. Let's convert 140. 140 minus the mu is what? 85 divided by 5. So that we do them at the same time on the table.
So 2.2.
This is 2.20. Okay, 2.2.
Yeah.
Right, greater than 2.2. Okay. So greater than 2.2 is the probability that we're looking. And let's go ahead and just dig from here. Get the tables. We are here finally already. Right. So we are looking for the probability of falling in between. That is between 1 and the -1, right? Which probability do you want? Is this one. So we found already the probability for this one, right? For after, because this table that we are using, it gives us the figures after the z value, right? For 1.00, we found this value, remember? Previously,
yes,
we found
1.587.
Yes, so it means this side there is 0.587. 1587. These numbers are starting with point, which means there is 0. Even this side, it was the same thing, 0.1587. So for you to find the area that is in between here, you just have to subtract these two figures from 1. Okay, the total area is 1, isn't it? The total area under this curve is 1. So you just say 1 minus 0.1587 times 2. Okay, they are equal, both on the right hand. You get the point?
Yes. 0.6826.
0.6826.
Yes.
Right. Exactly. That's how it is done. That's for the area in between here. In between. Or alternatively, you know that since this is 1, the right side can be equal to 0.5. Even the left side equal to 0.5. So since you don't have this number from here to here, but you have the number that comes after 1 here, this one, you can just subtract this number from 0.5. Did you get what I said? No. Like here from the center going to the right, 0.5, and going to the left is 0.5. So you can say 0.5 minus 0.1587. That will give you this area here, just this one. You get it, right?
Yes.
And then you do the same on the left side, it will give you for this area. Then you add those two areas as well. So you can do 0.5 minus this. What does it give us?
Me the same answer, 0.6826.
When you multiply it by 2.
Yes.
Oh, okay. So basically, that's how it is done. That's for in between. What about for 2.20? So you break down this as 2.2 and 0.00. So we have to check where there is 2.2 and 0.00. Where do they meet?
2.2 here.
And 00. Right.
You
followed?
Yes. 0.0228.
Yeah. This is the area that is after the z value. Now, where is the z value from 0? The z value is 2.5. It's somewhere here, 2.5. Then we want the area that is after the z value. The table already gives us the areas after the z value, which means this value here, it is already after the z value, which is 0.0228. It's already after. So the question is asking for the area greater than 2.5, which is the area after this. It is already 0.20228. That is the answer. For the area up, if they were asking for the area less than this, we would have subtracted this from 1 so that we can find all the area below before this going this side. Since we already have what is here. Is that clear?
Yes.
Any question?
No questions, but
You need to go through, right?
Go through, yes.
Yeah, you need to go through a bit again. Then you should be fine. When you listen to this recording plus that other one, you should be fine. Then you can still ask the questions by tomorrow again. You can still respond to you. Yeah.
All right. Okay.
Then the rest of the work is not giving you headache, obvious. It's not giving you a headache. Right.
Yeah.
The rest of it, because mainly I just wanted to communicate about this. This is the part that is a little bit giving a lot of challenge to others.
Yeah.
To others can manage to deal with the Bernoulli probability distribution by just substituting numbers, and then that
Mm-hmm.
can be okay. That is clear, isn't it?
Mm-hmm.
So with this one you already had the formula for this one. This one, you use this formula behind for the Bernoulli probability distribution, this one, okay? You use this formula for n factorial divided by k factorial times n minus k factorial. This is treated as one number multiplied by p to the power k plus q to the power n minus k. Where this is just as good as the combinations. I don't know the calculator that you're using. You know how to press factorial, like if you're using the Casio calculator on the upper left, there is a button that is labeled x to the power -1. So if you want to do factorial of any number, for example, 6, you can just say 6, shift, you press on that button, it will write something like this. Are you able to practice that?
I've seen where x to the power -1. Yeah, I've seen it, yes.
So press
So how do I use it?
number, then press the number, for example, 6, then you shift, press on that button. You're able to get that?
You said I press any number?
For example, 6. 6,
Okay.
press 6, then you shift, then you press on the button.
Oh, okay. Yeah.
What is the answer? Equals what?
It's giving me 6 and this thing.
And then press equals.
720.
Yeah. So that is the factorial. We read that as factorial. The symbol is factorial. So this is the formula that we use. Yes.
Oh, okay.
Where n is the number of observations. Okay. This n is the number of observation that we are given. Then P is the probability of succeeding in the experiment that you have. Whereas Q is given as 1 minus P. That's how they find Q. Q is just given as 1 minus P. And the N is the same number. Then K is actually the number that you are actually looking for. See the example now. See the example that we're going to. So let's identify the figures. According to the textbook, okay, 95% of the population has blood type B. Suppose that we choose 18 people at random, that is the sample size. So our N is what? 18 people. Then the probability of finding someone who has B, blood type B, is 9%, right? Which is 0.09. That's 9%. Then what is the probability that there will be 3? So K is our 3, okay? K is 3. Then we need the Q. Our Q, we said that it's 1 minus P. So in that case, it's 1 minus 0.09. What is our Q first of?
Mm, 0.91.
Okay, so Q is equal to 0.91, like that. So we can now use these into the formula, isn't it? The previous formula that we had, and calculate for the probability. This is the formula. Let's start combining into the formula. Our N is 18, so say 18 factorial divided by our K is what? 3 factorial times 18 minus 3, then factorial. Everything times the probability is what? 0.09
0.1
to the power 3 times
Mhm.
0.91 to the power what? 18 minus 3.
Mhm.
Have you seen the replacement? I'm just replacing into this form.
Yeah.
So when you do the replacement, what is 18 factorial?
6.40.
18 factorial. 18
Mhm.
factorial.
Said 18 shift then x to the power negative, then x -1, right?
Yes. It's a big number. Check there is times 10 to the power 15, which simply means the point has moved 15 times to the right. It's really a big number.
Okay, let me
So
do
let's
this.
do
18 shift. Still giving me 6 point.
here. Check to
What?
the right side. It is writing times 10 to the power a certain number.
Oh, times 10 to the power
That's the
15.
standard notation. Yeah. It's a very big
Mm.
number. Okay. Do the down one. 18 minus 3 is 15, right? So 15 factorial. What is 15 factorial times 3 factorial? We find the denominator. Let's do 15 factorial times the 3 factorial.
It's still giving me 7.84.
Okay, so how we are going to do it is like this. Press like this. 18 factorial, find the answer. Then you say divide the answer that you're going to find. You say divided by 3 factorial times 18, or is it 18? No, 15 factorial. Like this, you write it like, you just do it at once on the calculator. So you press 18 factorial equals divided by, open the bracket, 3 factorial times 15 factorial, you close. You close. Equals. It will give us the number, the answer. What are you finding?
You said times 15 factorial close bracket, then
15 factorial cross bracket equals.
okay. 816.
Yes, 816. So this is the answer that we put here. Okay. So here we put what? 816. So now 816 times 0.09 to the power 3 times 0.91 to the power 15. Okay, 18 minus 3 is 15. Yeah.
Times 0.91 to the power 15. 8.119.
816 times 0.09 equals to the power 3 is equal to that times 0.91 we close to the power 15. That is equal to what?
I found
find,
8 point.
do it again. You can do it in isolation. 816 times this one, you find the answer, then you say times this one. What do you find?
The first one, 816 times, is it
0.
times 0.9 to the power 3?
Yes, 0.09 to the power 3 is equal to, then times 0.91 to the power 15. You know how to tinika to the power? You say, you do this, right? Obviously, you know that. Like do 816, just the way how it is here, or type it like this. Then say equals. Then again, when you find that answer, then you continue typing this times this.
I'm still finding 8.119.
Okay, do this. Do them in isolation. Can you do 0.09 to the power 3? What do you find?
7.29.
7 point, let me see. 0.09 to the power 3. No, you don't count the you have not been counting the decimal places, I've seen. This is not 7. This is 0.4 decimal 4.00, another 0, then 729. That's how you report that. The calculator is giving you answers in scientific notation. So you have to consider that. Okay.
So 4
Then,
zeros, right?
Just 3 zeros. Yeah. So it was just giving you the right thing anyways. You could have interpreted it like that. So do it direct. Yeah. What do you find when you do it direct? Give me what you find.
It's giving me 7.29.
Okay. When you multiply with the times the 816,
0.59.
0.59 times 0.91 times, again continue, times 0.91 to the power 15. What do you find?
0.144.
0.443.
1445.
Okay, do this. Start from this far end. Can you do 0.91 to the power 15? You have found it?
0.243.
0.243 now. Times 0.09 to the power 3. You've done that? Then it times the 816.
0.1445.
Okay. Times 816. 0. Point what? 0.11. 0.14455. Like that. That is the percentage. That's the probability. So, but let me show you, there is a shortcut to find the 816. You can just press any K, which means it will be 18 combinations of 3, right? So you just press 18, then on the upper left, just the number to that button for factorial. There is a button NCR. So just press that one. It will give you, then you press 3 to give you the answer. 18, you press that button, neighbor to that factorial button, and then it will write 3, something like that. Then equals.
You said 18.
Then press on that button. Don't shift it, just press it.
It's giving me an error.
No, like you press 18, then you press on that button. There is this button which is labeled NCR. Just press 18, then you press on this button. Then you press 3.
Or 3.
Then equals.
Oh, 816.
Yeah, so that's the shortcut. Those are the combinations. You can just do that directly, then you get the answer. Right. So to answer the question, we can say that the probability is about what? 14%, isn't it? 0.144 something. So that's what is there.
Okay.